this webinar series has been a platform to exchange knowledge and information on NDE technologies in highway infrastructure. Also to inform researchers and technology providers and industry representatives about states' current practices and policies and about their challenges and future direction with regards to the use of NDE for condition assessment of highway assets. All the past webinars have been recorded, and the links are provided in the webinar flyer that is being distributed every month. Since 3 months ago, we switched the webinar platform from Adobe to Teams because many of you had difficulty registering and accessing the Adobe. And due to restrictions in sharing the files through FHWA Teams, we will be posting the recordings to the FHWA YouTube channel, which takes some time to get approval to get it posted. So meanwhile, until we get it posted on the YouTube channel, if anyone wants a copy of the webinar recordings from April, May, and June, today's webinar, please contact me directly and I'll be happy to share the file with you directly. Also, PEs who attend the entire webinar as an individual will be awarded 1 PDH. And to be eligible for the credits, you must remain signed in for the entire webinar, including the Q&A session following the presentation. So there's a survey after the presentation, and you will be asked to submit your email address. So please make sure to stay for the entire webinar. If you have any feedback, suggestions to improve this webinar series or suggestions for future webinar series or even guest speakers, please share it with us through the survey. So one topic that has been requested many times by the past webinars participants is NDE of timber bridges. So today our webinar is focused on NDE of timber bridges, and our guest speaker today is Mr. Jim Wacker, research engineer with the Forest Service Forest Products Laboratory, and he will share the techniques and tools recommended for NDE of timber bridges. So you can type your questions in the chat box and we will go over the questions after the presentation. So with that, I will pass it to Jim for his presentation. Jim?
Okay, good afternoon, everyone. Apologize for the technical difficulties. I did not anticipate them, so I was very glad to be invited by FHWA to share my experience with timber bridges with everyone today. I work at the Forest Products Lab in Madison, Wisconsin. It is the National Research Laboratory for the U.S. Forest Service and was established in 1910. I've been around not for all of that time, but for the last 25 years. My background is more from a researcher's perspective, and therefore my experience with inspection is based more on the numerous field studies that we've conducted on timber bridge performance and durability issues. We did a lot of work in the 90s on stress laminated or post-tension timber bridges for adoption by the AASHTO code. We did a couple dozen inspections of historic covered bridges in conjunction with FHWA and their preservation program. And more recently, we did a study where we looked at timber bridges around the country to look at the regional effect on durability detailing and service life estimation. We looked at a total of 132 bridges. So that's, in a nutshell, my perspective. Let's go to the next slide and see my presentation outline. To begin, I'll start out with an introduction on timber bridges and some of the key concerns. Then the meat of the presentation is the recommended inspection protocol, and then an overview of the tools we use for wood to non-destructively evaluate, or the toolbox that we have at our disposal. And then I'd like to go through 3 case studies kind of quickly that show the tools in action. and then answer any questions you may have. Next slide. Introduction, and the next slide.
Yes.
So wood is a naturally renewable resource. So it's a sustainable and unique bridge building material. It rejuvenates itself after service life. It deteriorates and returns to the environment. So it's got a lot of environmental advantages as it goes through the life cycle. Next slide. But that means because it's a biomaterial, it has some unique damage and deterioration modes, principally decay fungi and insect damage, which are unique to timber bridges. Drying defects are also concerned. This list shows everything. Fire is not so common, but it is a potential issue for timber bridges. More or less covered bridges are at risk for arson and fire more than regular bridges. So we'll go through some of this. Some of the other stuff listed here is applicable to all types of bridges, abrasion, wear, collision, and so forth. But moisture-driven decay and insect is what we're looking for. Next slide. So the two types of deterioration, again, are decay fungi and insect damage. And there's three types of decay fungi: brown, white, and rot. We're most focused on identifying rot that is brown rot because that type of deterioration or decay diminishes wood properties very fast, and the other two do not. And so that is where we're most keenly focused. The insects we're looking for primarily, there's several, are termites in only those locations near the coastal states on the Gulf, but sometimes a little bit farther away. And then carpenter ants are also, and they use the wood for food and or shelter. We'll talk a little bit about that. Next slide. So the biotic requirements for decay activity are important to understand, so I included this slide. There's four legs to the chair, I guess, to support decay activity, and it includes moisture, oxygen, temperature, and food source. The food source, again, is untreated wood. Treated wood is not a food source, and that's why we require treatment for all bridges according to AASHTO. But the temperature must be in a pretty good range between 50 and 90, and oxygen must be present. It's driven by oxygen and moisture, and so if something is underwater, like 10 feet or more, there's not enough oxygen, or if something is covered, like in a covered bridge application, then the moisture is not present, so it's usually less than 20%, and it's no decay activity. So that's important to understand. So some climates are not as conducive to wood decay, especially in the north where it's cold. Again, we talked about protective layer of preservative treated wood. These are some examples on the right. On the next slide, some examples of treated lumber that was cut down the section, exposing how much untreated wood can sometimes be on the interior. And that's where we're trying to look into with the non-destructive tools. We have to be aware that we want to limit the number of cuts and borings in construction to expose this kind of untreated wood without the protective layer, but we also want to be conscious of checks that can provide avenues for moisture or connections with drilled connections that connect the members that may funnel water into this untreated wood as well. So the whole idea being, many times the internal decay can be present without external signs. Next slide. And this goes on to the next slide, which is recommended inspection protocol. We generally recommend a 5-step field procedure. It includes a visual inspection to look for external indicators of decay, hammer sounding, followed up by moisture content survey, stress wave timing, and resistance micro drilling. Of course, we review previous inspection work to our target areas, but as we step through each one of these areas, especially 1, 2, and 3, we're marking locations where we have suspected decay, and we come back with the other tools to further investigate. And the last 2 tools are used very effectively to confirm the size and extent of decay on the inside of a member. Next slide. This just shows the example of some of the visual inspection that we go through. Of course, we use lights to see what we're doing underneath. We're looking for signs of damaged members, water infiltration through the deck, signs of debris impacts upstream. These are several bridges from our national study that I mentioned, but visual inspection is pretty straightforward. I'm sure many of you are familiar with that, but to look for signs in timber can be somewhat different than other materials. Next slide. So where do we look? Where do we expect deterioration? And in a timber bridge, it's usually where deck planks or decking members are fastened vertically with fasteners into the top of stringers. It's in cap members where we have drift pins between the cap and the pile. Anywhere there's a connection, end of the bridge where soil may be up against the end of the sawn girders or other type of girders. All of these types of connections or checks and splits on top surfaces provide the avenues that we talked about to get past the initial line of defense of the preservative. So that's where we look. Next slide. Are we on visual inspection indicators now? Yeah.
Yes, Jim, yes.
Okay, good. Just checking. Lots of things we look for: checked or split members, dirt and debris accumulation, signs of fruiting bodies, staining, discoloration, and of course, crushing impact. We talked about it, insect activity. Can't go through all of these with our time today, but I'll show you a few examples. Next slide, please. Here's an example of debris accumulation. So improper drainage on the right in the scupper opening underneath the curb, it supports plant growth. And so that's an obvious sign that there's too much moisture accumulating there and leading to premature decay in the scupper and the scupper block members, but also in the decking members at that edge of the deck. It's a critical area because that's where all the fasteners are for the guardrail system or the safety rail system over the bridge. So cleaning that out and keeping that effectively functional, draining the water off the bridge is important. On the left is the top of a pile where a check more than likely opened up accumulated water, debris got in there, and it supported plant growth. And so these are areas where you want to keep them clean. You want to protect the top of the cap members if it extends beyond the top of the deck. Very common place for deterioration. Next slide. Some very good pictures that show a fruiting body at the end of a lumber board. This is a treated board, so it's surprising that there's a fruiting body, but it's a very good picture of what a fruiting body looks like. It's an indicator of internal decay. On the right is a sunken face. This is a girder that had decay. It didn't drain effectively. It probably had debris and accumulation on top, and it trapped the moisture and led to very advanced total failure of that stringer, actually. Very large pocket. Next slide, please. since we talked about brown rot being so important, I wanted to make sure you understood what it looks like. It's darker brown in color. It takes the wood and it kind of crumbles it or cubes it all up into little crumbly cubes. And that's really the telltale sign of brown rot. And brown rot can visually be detected by an inspector, or you can take samples and send them to a laboratory to confirm you have brown rot. But this is what it looks like from the inspector's perspective. Next slide. This is a telltale sign of carpenter ant activity. Above on the cap member, there's some very small holes, but below it is a pile of sawdust. And this is indicative of carpenter ant activity. And in this case, the pile cap was no longer rectangular in shape. It had a big hollowing in it, so it was very ineffective and hollow and almost failed cap member. So that completes the overview of the visual assessment. Let's move on to the next slide and the overview of our NDE methods. Next slide. So this should show the equipment in cases. This kind of demonstrates the toolbox that we have available, and many of them are minimally invasive tools for gauging the internal integrity, again, of the timber members. Next slide is the first one is hammer sounding. Hammer sounding can be very effective. It requires some experience or some pretty advanced experience by the inspector to recognize the tonal sound of sound wood versus hollow or intermediate decayed wood. And it says it requires some skill. It requires more experience and skill. And so sometimes wet wood will appear to be decayed wood using the sounding, but we need to further investigate that, and we need to verify it with other techniques. Sometimes when you pound in with a hammer, it totally collapses, like on the bottom right, and you can punch it right through the wood. And so you want to make sure you know the extent of that deterioration. You can do that with hammer sounding or hammer picking as well. Next slide. So after we've done the visual and the hammer sounding, we've marked a number of locations to further investigate. We also come in with the resistance type moisture meters. These are based on the fact that the tips have a relationship between the electrical resistance and the moisture content of the wood. It's a very well-defined relationship. And the pins are about 3 inches long, but they're insulated with Teflon. And so they can measure at various depths. We typically measure at 1, 2, and 3 inch depths, so we can get inside that untreated wood, and we can find out how wet the interior is. Use a sliding hammer type action to install and remove the probes. And temperature increase and species corrections are required. Here's an analog example, but in next slide, the digital unit can easily punch those numbers in, and you don't have to deal with that. It's all adjusted automatically. But the idea is that elevated moisture content, typically over 20%, is a great indicator for decay potential. So usually, but not always, when the wood gets that wet, decay activity can take place if the conditions are right. And again, for bridge inspections, the 3 inch probes are recommended. You can get a lot of different moisture meters that have 1 or ½ inch probes, and that only gets within that preservative treated layer, and we're not looking for that information at that depth. The next tool in the toolbox is stress wave equipment. Here you see 3 different manufacturers of devices for wood. The MetroGuard unit is a United States manufactured one, but the other two are European. And there's information sources on all that. Next slide. The one that we use is the FACOP tool. We recommend it for use, for ease of use, because the transducer is connected to nail spikes, and so you just can quickly insert them, and then you hammer impact one of them. You measure the travel path or the transmission path of the member you're testing, and then you have the data that you need. It's a one-way transmission, but it does require, of course, access to both sides of a member, so it's not very conducive to install testing on a deck member where you have asphalt on the top, typically. So, next slide. Here's two examples of the stress wave tools. The one on the right is the U.S. manufactured one. It involves a hammer that's censored and a receiver that's censored. And you simply press the receiver against the wood and you hammer impact on the other side. And then on the left is that FACOP unit with the transducer spikes that we talked about. The use of the stress wave device is very localized data, so in order to understand the extent of things along a member, you need to develop an array of points and in order to characterize the extent of the decay. So it can be more time consuming than the other tools. Next slide. The last tool in our toolbox is the resistance micro drilling equipment, and this is the newest tool. It's only been around about 15 years for wood, originally developed for trees. It's a specialized tool. There's 3 suppliers listed here. We typically use the IML one. It's a German manufactured tool. The difference with this tool is it only requires one side access, so you can drill even against a concrete back member, and you can drill it to a certain depth, so it's very handy that way. But what's unique about this piece of equipment, next slide, it has a specialized steel needle. It's very small in diameter, so old-fashioned inspectors used to use about a 3/8 inch diameter and through bore members, and they would go by feel. This one uses a very tiny needle, and then the needle is so small, 1/8 of an inch, that it makes a hole that we don't even need to plug. We typically use the F400 at a 16-inch model, and you can get them even beyond 20 inches actually. But the idea is that the torque resistance in the drill bit, because the diameter is smaller, the torque resistance is all concentrated on the bit, and that torque resistance is related to the density of the wood. So let's look at what they produce when you're done drilling. Next slide. This shows a relative resistance density plot. It's non-scalar, but it shows the density of the wood. And so you can see you have sound wood on each side of a decayed zone in the middle. The decayed zone is typically when the resistance is 0 or very close to 0. But these up and down ridges are very indicative of the growth rings. And this slide is a good example. It shows that the early versions of the resistance drill were mounted on a portable drill. They've evolved, and now there's fully electronic units, which we'll take a look at in a couple of slides. Next slide. So if you overlay the relative resistance plot against a piece of wood that was drilled along the same path, you can see how when the grain orientation is perpendicular to the grain, it has very nice peaks and valleys that relate to the spring and the summer wood, or the rings of the wood. And then when the grain orientation switches they space out a little bit more, but they're still non-zero. If they were non-zero, that would be advanced decay. If they were close to zero, that would probably be some kind of intermediate decay. But the interpretation of these plots is somewhat tricky since we don't know the grain orientation in all cases, but it still is a very effective tool for finding inside pockets of advanced decay for sure. Next slide. This just shows the tools being used for sawn girder inspection. The one on the left, again, is the drill-mounted original version, and it draws the relative resistance plot on a wax paper. The one on the right is fully electronic, so the files are already electronic, and it has a number of bells and whistles. You can change the rotational speed. If you have a harder wood, you can slow it down to not overwork the engine and so forth, but it's got an entirely new drill casing, as you can see. It's quite handy in the new version. Next slide. So what does the new resistance drill produce? It produces this relative resistance plot. It shows in detail all the statistics about the drilling, and it shows where the resistance goes to almost zero, which in this case is about 1.5 inches at around 8 to 10 inches. You can see the drill path drawn on a pile cross section, and the decayed section is outlined in yellow. So it very easily picks up the internal decay. But not only that, it tells you the size of it within the cross section. The stress wave or the one-way acoustic doesn't necessarily tell you the size of that internal defect. But when you work together between that tool and the resistance drill, then you can start defining relative size in a section, which is important. Next slide. So again, I want to reinforce the 5-step procedure: visual assessment, sounding, moisture content survey. We mark locations for further investigation with stress wave timing and resistance microdrilling, and we can get the best idea of what's going on inside of members, the internal integrity. For more in-depth inspections or to support load rating analysis, we can do other types of things like core drilling and load testing and acoustic tomography. So I'll go over those very quickly. Next slide. Here's a picture of a load test we conducted on a 1960s era timber bridge in Washington State on the Gifford-Pinchot National Forest. It has a glulam deck that was replaced recently, but there's some concern about the glulam girders because they were manufactured way back when in the early days of the industry. And so we attached a whole bunch of fancy transducers to measure dynamic loads as the vehicle crossed. But in addition to that, we set up an optical survey and we put rulers hanging down from each girder. So that's something an inspector could do quite easily at the county level without too much cost, and measure the deflections of a bridge and get more of the system response. Is one girder not performing well compared to the others? Next slide. Acoustic tomography is the last tool I'll talk about that we can use. It's very suitable for wood piles, round members. It can be used for square members, but it's a little bit more challenging. But it's based on the same concept as the stress wave timing, that the timing takes longer for wood that is traveling around an internal void. Is that screen moving as the waves propagate? I can't tell from this end. Probably is. Let's go to the next slide, the one that says Picus sonic tomograph. Here you can see it's several sensors that are arranged around the perimeter of a tree trunk. This is where it's used quite extensively, but again, it's totally adaptable to piles. And as you install those, you tap each sensor successively, and all the other sensors receive the hammer-impacted acoustic wave. And so the computer software assembles these tomographs, which gives you a very high reliable image of the internal integrity. And as you might imagine, the more sensors you have around the perimeter, the better the image quality or the reliability of that internal condition. So that gives you an idea of one manufacturer's use of acoustic tomography. Next slide. I wanted to mention ground penetrating radar. This is something that we're investigating right now to inspect timber bridges, and it's well known, of course, with concrete bridges to be very effective at inspecting. We're trying to tune it to use in timber bridges. Can we change how we collect data? Can we change how we process the raw data to get a look inside of timber components in a bridge? And the advantage that we're going for is all the tools we talked about so far are point-based data. We have to mostly develop an array, and we want to move towards more scanning type NDE technology. So this is one effort we're doing right now. You can see we have some artificially decayed specimens here that we're testing in a laboratory. They have some drilled holes, some wet sawdust inside, and we're trying to detect them with the radar. We're also looking at things like moisture content and treatment chemicals. And then the next stage, the next slide, please. We're exposing some specimens that were inoculated with brown rot. Brown rot is that very concerning type of decay we talked about. And in this case, we're using Douglas fir specimens, so we chose a brown rot fungus that is very aggressive, and we're trying to put these in a very decay-prone area for wood structures of the United States, and we're trying to develop internal decay so that we can get some naturally decayed specimens that we can proof or test our ability to use GPR to look inside of members. And so we have about 100 specimens that we started with a few years ago. We bring about 8 of them back each 6 months, and we scan them, and we cut them open, and we do further testing here at the laboratory. Again, trying to benchmark how well we're doing with looking inside with GPR as the decay progresses from sound wood to internal decay. So hopefully that'll be a tool that we can add to the toolbox very soon. It's very effective at detecting moisture, obviously, and that is useful in itself, but we want to be able to detect internal decay, the earliest signs. So next slide. Now I'd like to move on to the case study. The first one is a bridge substructure. Next slide. The East Deer Park Bridge we worked on about a dozen years ago in Gaithersburg, Maryland. We worked with some cooperators at Montgomery County and URS Engineering. Next slide. This shows just an end view picture of the bridge. It's quite a unique bridge. It's an arched bridge. It's right at a T intersection. It has signals on each side, so only one lane of traffic can cross at once. Next slide. The East Deer Park Road Bridge has 2 timber frame vents supporting the bridge. Steel girder bridge with glulam transverse deck panels on top. It's actually a railroad that goes underneath. And we were brought in by URS to look at this timber frame bents, primarily to look at the level of interior deterioration, but also they were concerned about the deep checking going on in some of the columns and the potential for structural implications from that. So we went out there for a couple days in a very rainy season. Next slide. We worked for 2 days inspecting both of these bents, and we had to be very wary of the train. It came at a very high speed, so we had to clear the area. But the time of the inspection was also a very rainy day, so we got to see where water moved off the bridge and through the deck, and that was very telltale. But here we're in the middle top investigating a cap beam using FACOP. We're also on the left cataloging and measuring the depth of the checks using a series of feeler gauges, so we can measure the depth, the length, and the width of those openings, and then compare them to industry standards for reductions due to checking. Not too many reductions for columns. In bending, it's different, but the checking didn't seem to be too big of a concern. And then, of course, we're collecting moisture content and doing visual inspection. The next slide, please. This is kind of a summary of all of our field inspection work. We, using our 5-step procedure, came up with these areas as having problems. 2 areas were in the cap beams on the top. They both had checks opened up on the top and water infiltrated. So one had more advanced decay than the other. And then in a couple of areas on the columns, we found some small decay zone and some splitting. So based on our recommendations on this level of deterioration, especially the cap member, next slide, please. The county made a decision to replace the timber frame bents. And you can see here, I talked about water intrusion. The day that we were there, we could visibly see water falling from the crack between the panels, which was directly aligned above the cap member. And remember, the bridge is an arched roadway, so those panels at the joint kind of almost funneled water into them if the asphalt cracked, and then it deposited it right on the cap member underneath, leading to some corrosion on the steel, but also deteriorating the cap beam member. So again, the county made a decision to replace the frame member. Next slide. The next day after we completed our work, the URS engineers conducted some live load testing, some proof loading, diagnostic load testing, where they instrumented all of the steel girders with strain gauges. They looked for the live load distribution. Let's go to the next slide. These are BDI type sensors. They're specialized strain sensors that were attached to the top and bottom flanges of the steel. And you can see through the relative magnitudes of the girders how the live load is distributed laterally across the bridge. This is just one example of a load case. They ran it through, on the next slide, a full engineering analysis using a modeling and finite element procedures for both the substructure and the superstructure. And the general conclusion they came to, I believe, was there was some limiting factors in the steel stringers, which were quite small on the approach spans, and then the cap beam on the timber frames was a controlling factor as well, especially with the level of deterioration that we reported. So next slide. So they made a decision to replace it. Here's a picture of the new Southern Pine treated frame bent installed. But because they made their decision, that gave us an opportunity. Next slide. we asked them to ship the materials to our laboratory in Madison, and that gave us the opportunity to re-inspect these members while they're not in the bridge, and so that we could inspect using our tools at a 1-foot interval along the entire length of these members. A very intensive scan. Next slide. And so by doing this, we were able to take a very close look at what we did in the field and see if we could confirm it. And if you hit the enter key one more time, I think you'll see the overlay of the results from our intensive scan. It pretty much validated the information we collected in the field with some areas of decay pockets located in those cap members. So let's go to the next slide. This is laboratory full-scale testing. Not only did we do the intensive NDE inspection, but we were able to reconstruct the frame bends in the laboratory, and using the information from the live load test that was conducted at the actual bridge, we applied different loads to these columns. We have an actuator over each column, simulating where the steel beams sat. Next slide. And we're able to apply different types of live load vehicles, not only the actual field test vehicle and compare the results, but also HS-20 and other rating vehicles. And you can see the applied loads on each of the columns, pretty significant loads. And in all that, the columns did very well, very low levels of strain measured. The cap member did have some excessive compression in those areas where we reported the internal decay, but certainly did not fail during our test. Next slide. The next case study is a historic covered bridge. Next slide. This is the Indiana Historic Howe Truss Covered Bridge. For this project, we worked with cooperators at Iowa State University and FHWA. This is, I believe, a bridge in Park County, Indiana. Next slide. So our focus for covered bridges, since we talked about it before, most of the members are very dry. We focus more on material properties. And we used the FACOP tool in a little bit different way, where we can use it to estimate the MOE, or the elastic modulus, of certain key members to support some of our analysis or modeling for the entire bridge. And so if we measure a stress wave velocity in a parallel to grain orientation, we get also a density measurement. We can derive the MOE with a very high degree of accuracy. We also collected core samples to identify species and the density in the laboratory. This speaks to the grade of the wood. And so when we go in to assign a value from the design code, we can do it more reliably, rather than using so many assumptions. And again, we're doing the moisture content surveys and the resistance drilling. Typically, on a covered bridge, we only see moisture elevated or deterioration near the end of the bridge, as vehicles carry moisture onto the bridge. And those components see the most deterioration and have to be replaced periodically over the life of the bridge. And so that's what we're doing here. You can see the new resistance micro drilling unit being used to go through some bottom tension cord members and look for internal deterioration at that support area. Next slide. And this shows us measuring the top chord for this Howe truss and using the FACOP. I think the distance between the two is about 12 or 13 feet. But again, you measure that distance very precisely, and you simply get longer cords for your sensors so that you can stretch between those 2 points, and you hammer tap a few times and you get your timing. to derive your MOE for those cord members. Next slide. The last case study I'll talk about is this historic mine building. Next slide. It's not a bridge, but most of what we're talking about in terms of inspection and the 5-step field procedure applies to building wood structures as well as bridges. The only difference here is there was no preservative treatment on this wood. The historic copper mine in the state of Alaska. It's located within the largest national park we have, the Wrangell St. Elias, and the National Park Service is the current owner. It was a mine that was built in 1910 or so. This is the concentration building. It's built along the hillside next to a glacier in the valley, right, very close to it. And the mine came in at the copper came in at the top in buckets, and it produced iron ore at the bottom through a very water-intensive process using gravity, of course. Next slide. This is the conditions in 2009. So it was built in 1910, but in 1935 it closed. They ran out of copper in that location. So it sat vacant and open to the elements for many decades. In the 1970s, the Park Service acquired it. They started putting some covers on the top layers, but it went through years of deterioration and neglect. And so we were brought in because they're trying to restore all of these buildings in this historic mining town. And it's quite a tourist attraction as well to bring folks through here. So that was the whole emphasis behind it. These are the conditions of it in 2009. You can see on the top right the exposed foundation. That was the focus of our efforts. It's a timber crib. It uses Doug fir. It's rock filled. So it's a native soil filled timber crib. It stair steps up the hillside, and that's what we mostly looked at. Next slide. Here's all the tools in use, visual inspection on the bottom right. Some of these walls were 10, 12 feet high, and some of them were only 2 or 3 feet high. There was, I don't know if I mentioned, but there's 11 different stories in this building. It seemed like there was several additions added as they went for different stages of the process. The lower levels, if you can believe it, were wet, and they were sometimes frozen, so some of the drilling was not very conclusive in the wet wood. It's something we never drilled before because it was frozen, and we were up there in June, so it may stay frozen for most of the summer at the lower levels that are closest to the ground. The upper levels were not frozen; they were more open air. Next slide. One thing that we did up in Alaska at the mine was we took several core samples from levels of the timber cribbing. And we largely found soft rot, which is not too much of a concern, and it's indicative of this water-intensive process that they used. So excessive moisture above the saturation point can kind of protect the wood from decay. Again, it's very cold up there, and the Doug fir that they used was old growth, so that has some natural durability to it as well, since it was not treated. But we did find a few instances on level 3 and on level 5 of brown rot, and you can see those examples in the microscopic images at right, some of the telltale hypha and indicators for brown rot. Next slide. This shows a schematic summary from the lower 2 levels, level 1 and 2. This is the kind of information we provided in our report to the National Park Service, and it shows that there was some severe decay in level 2 in the dark red. There was advanced decay all over the place, especially on level 2, and the yellow and the blue are not so concerning, but the higher you go up in this building, the more decay you saw. And so based on these results, the Park Service made some plans to go through some replacement portions of the timber foundation, but they also did some stabilization procedures. That was a few years ago. I don't know how far along they are, but they're stabilizing to make it more safe as they bring the tourists through the building and to show them the historic copper mine. Next slide. And then one more next slide. So that kind of concludes my talk and the 3 case studies I presented. And I wanted to just summarize so that the whole idea of inspecting for timber is not to rely solely on visual inspection methods. They don't tell the whole picture. If you use a 5-step procedure, you can, which is recommended, you can take a really good look inside and get a better view of what's going on. There's tools, NDE tools available for looking at the internal integrity. You can assess material properties with some of the NDE tools. And there's several resources available through this. We did a recent study with the University of Minnesota that focused on inspection, and it was done in the wake of the I-35 bridge collapse, so they were very well interested in getting up to date on their timber bridge inspections. So those resources are available. And of course, the outcome is a more reliable inspection than just visual. Next slide. So that's there's several publications available, and here's some joint publications that I talked about. They're all available at our woodcenter.org website, or our national center. And the most recent publication that's been updated, I guess, is probably this Wood and Timber Condition Assessment Manual. It has a nice description of each tool, how to use it, and so forth, but several publications. And then one more click should be my last slide. Thank you very much for your attention. And if it works out, I'd like to answer some questions.
Thank you so much, Jim. I apologize for the technical difficulties that we've had and going over the hour. And I'm so sorry, Jim, that you had difficulty getting into the room. It must have been frustrating not to see the slides. And I had to mute myself so that you couldn't hear my kids screaming. So, but it worked well at the end. It worked very well. We have some time, like maybe 5 minutes, to go over the questions. Let me go to the chat.
There's a question in the chat. So it says, are there natural substances applicable as protective coatings to minimize environmental issues for in situ use? And then the second part is, can cedar timbers be used as natural insect resistant timbers? As it is FRP wrapping an applicable retrofit of damaged columns or bends?
Yeah, I didn't catch the first part, but the cedar has been used for bridges. It is an AASHTO-approved species that can be used without preservative treatment. I would say most people are using it in a northern environment where the decay potential is not so high. I know of some bridges in Alaska where they're using Alaska cedar. I don't know that it provides very good protection against insects of all types. Of course, bear damage is a concern for cedar. They scrape it all up. It's a very soft wood. But the protective coatings are something we looked at. We generally protect the deck with an asphalt waterproof system, and we're trying to develop ways where we drain the deck more effectively, where we get the water past the curb and scupper and the edge of the deck with flashing so that the entire deck remains relatively dry, or as dry as we can keep it, similar to a covered bridge but without the cover. So and the FRP has been used as wrapping, but you want to make sure that whenever you do any type of protective wrapping that were not making conditions worse. And so if water gets in that wrapping, it doesn't breathe and it can't dry out if water gets in, and it will actually accelerate the decay potential. But yeah, FRP is an option, but you have to be very careful.
The first question was, are there natural substances applicable as protective coatings to minimize environmental issues?
This is a big area. The preservative treatments, creosote is still used, but not in a lot of areas. Pentachlorophenol is the next one, but that's going to be limited use very soon, I believe. We generally recommend an oil-type preservative for durability purposes because that has the best track record at repelling moisture and stabilizing the wood in service. And so it's the most durable treated bridge option. However, in pedestrian applications and more, there's pressure to use waterborne preservatives. These are largely copper-based preservatives. And what that can introduce is some potential corrosion issues between the treated wood and galvanized components. And it also, if you talk about waterborne preservatives in glue lam members, that's where the laminations are glued up into very large beams. It can promote checking, and in some cases, excessive checking in service. And so those are some concerns. So if all possible, we still recommend an oil-type preservative. One that is very favorably reviewed by EPA and their regulations is the copper naphthenate. And so that would be a good option.
And Vincent has another question that if it's, he's wondering if linseed oil is effective.
I don't have too much experience with linseed oil. I saw it being used on a bridge in Japan, and they use it in a traditional sense over there. They reapply it every few years, and so from the maintenance and the cost of that here, I don't see that really being an option because there's usually very few dollars for maintenance and those type of activities.
All right. Any other questions? I don't see any other questions. I posted the Teams form, the survey form. Please fill it out. Leave your feedback and your suggestions for future topics. And also, if you would like to get credits for one PDH, I would like to get the certificate, fill out the form, please. It's in the chat box. Wins as another question, have modal testing techniques have been used for as an NDE type indicator of damage or deterioration, either for global or local?
I'm sorry, I didn't hear the first part of that.
Have modal testing techniques been used as an NDE type indicator of damage or deterioration?
This is vibration type modal?
I believe so, yes.
Yeah, we've done some work in this area, and it's certainly done by a member, individual members, but that's more into production of components in the manufacturing facility. You can assign properties very effectively using modal. In a bridge, though, it's quite different, and you can get a system response, and you can use it to indicate problems in a bridge, not necessarily identifying the problem area, but you can detect there's a problem, like say a entire girder out of a multi-girder system is distressed or failed. We've done some work in there with forced vibration and with free vibration, but it's not, how do I say, you have to add mass to the timber because it's so light, and to get an effective response, you have to add all these weights. But yeah, we do have some reports available about that.
Thank you, Jen. Any other questions? I don't see any other question. Um, so probably we can adjourn the webinar. Again, sorry that we had to go over the hour. Sorry for the technical difficulties. But thank you so much, Jim. Great presentation. I personally learned a lot from your presentation. And thanks for sharing your experience with NDE of chamber bridges. And thank you all for participating in another webinar. The next webinar will be on July 26th, which will be focused on application of NDE on pavement. The presentation will be delivered by FAA, I believe. So I encourage all of you to attend the next webinar. Again, be on the lookout for the next webinar. You should have a link to the webinar. But if you don't have it on your calendar, let me know. I can forward it to you. And Dennis asked about a copy of the presentation. Sure, yes, I have a copy of the presentation. I will share it with everyone on the meeting invite. So with that, I'm going to adjourn the webinar and wish all of you a great week. Thanks, everyone.